everyone, I'm Julie.
And I'm Devin, and today we will be discussing how to make a buffer for Dwayne the Rock Johnson swimming pool using boric acid.
So to create this buffer for a swimming pool, we will be using boric acid, which is a weak acid, and adding it to water, which will yield the conjugate base of the weak acid, which is dihydrogen borate. And H2O will yield H3O+, which is hydronium. So throughout this reaction, we will also be adding potassium hydroxide to test the buffer capacity for our pool solution. We'll be calculating the pH after every step of this process.
So here our first question is, a buffer is made for a swimming pool by using 2.133 grams of a 230 milliliter solution of boric acid and KOH, which is potassium hydroxide. And we're told to calculate the initial pH of the buffer. We are given the molar mass of boric acid, which is 61.84 grams per mole, and we are also given this acid's Ka value of 5.8 times 10 to the negative 10th. The chemical formula for boric acid is H3BO3. Now we're going to write the chemical equation for our buffer. We're going to start with boric acid, H3BO3, it's an aqueous solution, plus H2O liquid, which is water. And this is going to turn into our first conjugate base, which is H2BO3 minus aqueous, this is dihydrogen borate, plus our hydronium, which is H3O plus in an aqueous solution. Now that we have our chemical equation, we're going to start with some conversions. So first we'll need to find the moles, and to do this we'll be putting the mass of our solution, boric acid, over its molar mass, 61.84. And this will give us the total moles of our boric acid solution, which is 0.0345 moles. Our next conversion will be milliliters to liters, and we'll do this by dividing our total milliliters of solution by 1,000, and that will give us a 0.230 liters of solution. Now that we have these conversions, we can use them to find the molarity. The molarity formula is moles of solute over liters of solution. Our moles of solute here are 0.0345 moles over 0.230 liters, and that's going to give us a molarity of 0.150 of boric acid. So here we'll rewrite our chemical equation without our solids or liquids because they won't have their concentration in the form of an ice table. And we'll put in our initial values, and our only initial value that we'll have is boric acid at 0.150 molarity. And then we'll put in our change in values, which is going to be minus X for the reactants and plus X for the products. And then we'll add those together in our final line. Using our chemical equation, we'll make our Ka quotient, which is going to be our products over reactants. So in the products, we'll have H2BO3 minus times H3O plus over our reactant, which is boric acid. And we were previously given our Ka value, and we'll write that in here. That's going to be 5.8 times 10 to the negative 10th. And then we'll restate with our concentrations that we found from our ice table. It's going to be x squared over 0.150 minus x. But that minus x here, we might be able to remove through ionization. To solve for ionization, first we'll have to find x. Now that we have our x, we can solve for our percent ionization. To do this, we'll put our x value, concentration, 9.33 times 10 to the negative 6, over the molarity of boric acid, which is 0.150 molarity, and that equals 6.2 times 10 to the negative 5th, which is a very small number, And even when we do the percent conversion times 100, it'll be still less than 5%. So we can get rid of that x value in the denominator. Now that we've found our x value, this is the same as our hydronium ion, so we can start solving for pH. So since this is our concentration of hydronium, if we do negative log times the x value, which is 9.33 times 10 to the negative 6, this will give us a pH value of 5.03. Since we haven't yet added any of our potassium hydroxide or any hydroxide ion, our predominant species is still going to be boric acid for the first region.
Now we're told to calculate the pH in region 2 given the same information for boric acid, and we are adding 30 milliliters of 0.05 molar solution of potassium hydroxide. So in order to do that, we have to still convert milliliters to liters, and we're going to do that by dividing by 1,000, and we're going to get 0.030 liters. There's the O somewhere. There we go. Don't forget your sig fit, guys. They're really important. Anyways, we're gonna get 230 milliliters, and we're gonna divide it by 1,000 in order to get the liter conversion, which is 0.230. Now we're gonna find the moles of potassium hydroxide, and since we're given the molarity, we're gonna go ahead and do 0.05 molarity equals x moles over 0.030 liters. After solving for x, we're going to get 0.0015 mole of potassium hydroxide. To find the new molarity of potassium hydroxide, we're going to take the new moles and we're going to do 0.0015 mole over the total new volume, which is 0.230 plus 0.030 liters. And I'll simplify here that the liters added together is going to be 0.260. And if we divide 0.0015 mole over 0.260 liters, and I forgot a zero there, it's going to give us 0.00577, round it up. Now we're going to do the same thing that we did for potassium hydroxide, solving for the new molarity of potassium hydroxide. We're going to do it for our boric acid. Our molarity for boric acid is 0.13269. Using the molarities that we just calculated, we're going to go ahead and plug them into the ice table. And for the initial concentration for boric acid, it's going to be 0.13269. For potassium hydroxide, it's going to be 0.00577. And it's going to yield dihydrogen borate, which is just 0. And then we're going to subtract 0.00577 from the boric acid concentration. We're going to do the same, subtract it from the potassium hydroxide concentration. And we're going to add it to the dihydrogen borate, which is going to be 0.00577. As you can see here, our limiting reactant is the potassium hydroxide. Once we subtract those values, we get 0.126923. We're going to get 0 for the potassium hydroxide, and we're going to get 0.00577 for the dihydrogen borate because you add it to 0, obviously. And then we're going to use those numbers and plug them into the Henderson-Hasselbalch equation. And it is pH equals pKa plus the log of base over acid. So plugging the values in, we have to find pKa, and to do that, we're just going to take the negative log of Ka, which is 5.8 times 10 to the negative 10th. To finish computing our Henderson-Hasselbalch equation, we're going to add log of base over acid, which is 0.00577 over 0.126923. strong base in this buffer be like?
Pride, it's about power. We stay hungry, we devour. Put in the work, put in the hours, and take what's ours. Like in some more in my veins.
This gives us our new pH of 7.89, and our predominant species in this region, which is the second region, is the boric acid. The predominant species of this reaction is going to be the boric acid because the limiting reactant was the potassium hydroxide, which was consumed completely.
Here, solving for our third region, we're going to be finding the pH of our buffer at equivalence point, and we're given a new volume of 690 milliliters, and our solution is the same molarity at 0.05. And first, what we'll do here for our potassium hydroxide is we need to find the moles so that we can convert back to our molarity later with a new value. So we'll set 0.05 moles molarity equal to X moles over 0.690 liters, and we got this volume from 690 milliliters divided by 1,000 liters, and that'll convert there. And our new moles are 0.0345 moles of potassium hydroxide. Now we're going to do the same thing we just did, finding moles for our boric acid. And to do this, we're going to be setting our concentration of 0.150 molarity equal to X moles over our new converted volume, 230 divided by 1,000 liters is going to give us 0.230 liters equals 0.0345 moles of boric acid. Now that we've got our moles, we're going to be finding our new volume using the volumes that we had previously and adding them together. So 0.690 liters plus 0.230 liters is going to give us 0.920 total liters. Now we'll use our moles that we found in an ice or broad table. Here it'll be an ice table. Our initial values are going to be the same for both boric acid and potassium hydroxide, 0.0345 moles for the initial value. And we'll start with 0 moles of H2BO3 minus. Now for our change in concentration, since we have a strong base and a weak acid, they will combine entirely, consuming all of both of them, so minus 0.0345 from our reactants, and then we'll add 0.0345 to our products. Next, we'll make a new ice table of the reverse reaction now that we've finished calculating our moles. And to do this, for this table, we'll be using molarity, and we'll be using 0.0345 moles over 0.920 liters, and this will give us a molarity of 0.0375 for our dihydrogen borate. And we'll have no initial values for our products, boric acid or potassium hydroxide. To continue our ice table, we'll subtract X from our reactants and add X to our products. We don't yet know the X value, and our change in equilibrium here will be 0.0375 minus X for the reactants, and then for the products it'll be just X. Since we started off with a base, we'll be constructing our reaction quotient using Kb, which we'll solve in a moment here, and we'll do our products, which is our boric acid and our potassium hydroxide over dihydrogen borate. Now to solve for Kb, we'll be using our water constant Kw to get Kb from Ka. So this will be Kb equals Kw over Ka. Now to find Kb, we'll use our water quotient, 1 times 10 to the negative 14th over our Ka, 5.8 times 10 to the negative 10th. And we'll get 1.72 times 10 to the negative 5th. Now that we've found our Kb, we're going to set up our equation to solve for X. Here we'll assume our percent ionization for dihydrogen borate is going to be very low, so we'll exclude that from our equation. Solving for x, we get a value of 8.04 times 10 to the negative fourth, and this will be equivalent to our potassium hydroxide concentration, and we'll later utilize this to find pOH and then pH. To find pOH from our OH concentration, we'll take the negative log of that value, 8.04 times 10 to the negative fourth. We'll get a pOH value of 3.09. To get pH from this, we'll subtract 3.09 by 14, and that'll give our pH of 10.9. For region 3 here at our equivalence point, since both species are equal, there will be no predominant one.
Last but not least, for region 4, we are told to calculate the pH of the buffer after the equivalence point when 730 milliliters, of course we have to convert it to liters, of a 0.05 molar solution of potassium hydroxide is added. Of course, we're going to identify the predominant species in this region, and we are given the same information about the boric acid like we have before. Now we're going to find the moles of boric acid given the molarity and the milliliters that we converted to liters. We're going to go ahead and do 0.150 molar. We're going to equal it to X mole that we're trying to find over 0.230 liters, which is going to give us 0.0345 mole. We're going to do the same thing for potassium hydroxide given 0.050 molar. We're going to equal it to the X mole that we're trying to find and our 0.730 liters that we converted from milliliters by dividing by 1,000. And that is going to give us the X value of mole that we're trying to find, which is 0.0365 mole. Our chemical equation, which is boric acid plus the potassium hydroxide, which is yielding dihydrogen borate, that will be our chemical equation. And then we're going to set up the ice table and we're going to compute the moles that we had just solved for. So our initial for boric acid is 0.0345. For potassium hydroxide, it's 0.0365. And for dihydrogen borate, we had none. And then we're going to subtract the boric acid, which is 0.0345 from the reactant side, and add it to the product side. And then it's going to give us 0 for the boric acid. It's going to give us 0.0020 for the potassium hydroxide. And then it's going to give us 0.0345 for the dihydrogen borate. As you can see, the limiting reactant is our boric acid since it was consumed completely in this chemical reaction. After we subtracted the mole of boric acid from potassium hydroxide, we are going to get 0.0020 mole, and then we're going to divide it over our new volume, and we're going to get 0.002083 molar of potassium hydroxide. To find the pOH, we're going to plug in our concentration of KOH into negative log, and we're going to get 2.681, and then we're going to take the pOH, subtract it from 14, so 14 minus 2.681, we're going to get 11.3 as our pH for our fourth and last region. In region 4, we have completed our chemical reaction, and our predominant species in region 4 is going to be our potassium hydroxide. So me and Devin here, hi Devin.
Hello.
We're going to explain to you guys the titration curve that we just did with our chemical reaction.
At our initial point, we hadn't yet added any KOH, so we'll have 0 liters added for our x-axis, and this got our pH on the y-axis up to 5.03.
And then for the second region is going to be before the equivalence point, and then for the x-axis we're gonna have 0.030 liters, which is not that much, and then we're gonna have 7.89 pH. This is gradually adding the KOH.
Our third point, equivalence, is when we had an equal amount of KOH and boric acid right there. We had 0.690 milliliters or liters, 690 milliliters of solution.
Liters.
And then we got a pH of 10.9.
And then for our last and final region, which is after the equivalence point and after the KOH is fully in there, our liters is going to be 0.730 and our pH is going to be 11.3. And this is just showing you guys what the points mean on the graph. So the left one's the liters, the X one, and the one on the right, which is Y, is the pH. And we have highlighted exactly where the regions are. So right here we have region 1.
Region 2, right here in green.
And then over here in blue we have region 3.
And then region 4 after we reach our equivalence point. Thank you for watching. We hope you've enjoyed listening to our buffer about Dwayne "The Rock" Johnson's swimming pool.
And I hope that we helped out Dwayne "The Rock" Johnson's pool staff on getting the right buffer solution.
And we hope you've learned a little something along the way.
All right. Bye. I mean, I don't want to either.
Okay, we're doing it.
It's about drive, it's about the power. We stay hungry, we devour, put in the work, put in the hours, and stay good hours.
Range, my culture banging with strange. I change the game, so what's my motherfucking name? What they gonna get though? Desecration, defamation.